Moving into Chapter 8, we're talking about polar coordinates, and then we're going to talk about vectors. What we've done so far has been a review for a lot of you. This may be some new stuff. When we're talking about polar coordinates, we talk about using a polar axis. Now, this section does not introduce the polar graph. We kind of have to sketch our own, but I will make available for you practice pages potentially where you have the polar graph. You can see that we have our XY axes, but superimposed on that we have basically a bullseye where we have circles that are concentric so that the distance between each circle is exactly the same. When we're dealing with polar coordinates, we want to kind of redefine our axes so that the origin of our graph, where the x and y axes intersect, is now called the pole, and the positive x-axis is what we call the polar axis, and we're going to think about rotating this polar axis around the pole. So think about graphing for just a second before we get started filling in. If I have a point on my graph, let's say I put it right here. I have this point on my xy coordinate plane. How many sets of coordinates define where that point is? How many sets of coordinates? How many xy pairs will define the location of this particular point in my xy coordinate plane? Well, just one, right? And we know some things. We know that because we're in quadrant 1, that our x and y coordinates are both going to be positive. They look fairly equidistant, maybe it's hard to tell. It looks like maybe that could be on a 45-degree angle, right? Because it looks close. But I've only got one set of coordinates available there. What if, though, instead of just putting a point, what if I took and I drew a line through that to represent an angle? Well, how many angles theta could this define? Well, while this point is just one set of points, one set of coordinates, just one point, this could be an infinite number of angles because I talk about rotations, right? It could be just this, so let's say that's 45 degrees or pi fourth. Or it could be this, which would be 9 pi fourths, or I could just keep going. Or I could choose to rotate in a clockwise direction, which would make infinite number of negative values of theta. So depending on whether I'm focusing on this as in the xy coordinate plane, where I have a set of xy coordinates, or thinking about it as an angle, it can be defined differently. Okay. Unlike rectangular coordinates xy, polar coordinates are in the form r theta, which represents r is my distance from the pole, and remember the pole is that center. We've always thought of it as the origin, and theta is the angle that is generated from the polar axis. So I am taking this positive x-axis and I am rotating it either counterclockwise or clockwise, however many rotations. So we're going to plot polar coordinates in the form r theta. We're supposed to plot 3 60 degrees by first drawing an angle of 60 degrees. And then from the terminal side of this angle, we're going to draw a number line and mark out 3 units. So when I'm doing this, I want to follow that order. I want to always find the angle, find theta first, and then I'm going to figure out where r is. Find theta first and then figure out r. So if I want to graph 360 degrees, that's my polar coordinate, I'm first going to find 60 degrees. Well, 60 degrees is, let's say right here, would be 60 degrees. And then I'm going to mark off, think about those concentric circles like I showed you, that bullseye. 1, 2, 3, 4. I would keep marking off where circles would hit. we want positive 3. So if this angle is 60 degrees and then I go 1, 2, 3, there is the point that is 360 degrees. So theta is 60 degrees and then I go positive 3 along that 60 degree angle. Now it does not matter if I measure angles in degrees or radians when I am doing polar coordinates. The value of r can be positive or negative. Now this is why it's important to do your angle first, because if r is negative, you move in the opposite direction. So you still find theta, but if r is negative, you're going to move in the opposite direction of the terminal side of the angle. Move in the opposite direction of the terminal side of the angle. So for example, this we graphed 360 degrees. What if we want negative 360 degrees? We still plot, or we still graph 60 degrees as theta. Theta is still 60 degrees. But instead of moving in a positive 3, I want to move negative 3. So this is the terminal side of my 60 degree angle. I am going to go back this way. I need to go negative 3, so I'm going to mark off 3 units in the negative direction. This is the point, negative 3, 60 degrees. Okay. Plot the point for 2 pi thirds. Well, I need my axes with my pole and my polar axis, the positive x-axis, and I'm going to move first to 2 pi thirds. I find the angle first. 2 pi thirds falls in the second quadrant, so we're going to be right about here. This is 2 pi thirds. Theta is 2 pi thirds, and we want to go to 4, a positive 4. So I'm going to mark off 1, 2, 3, 4. Think about where those concentric circles would fall, and there's the point I need to graph. Polar coordinates. And then remember, since these are polar coordinates, this can represent infinite number of angles. So it asks us to represent the location of this point in at least 3 other ways. The first set of coordinates that would represent this angle would be 4 2 pi thirds. Well, another set of coordinates could be if I go around again. So I could also say 4, and then if I add 6 pi thirds, I would be at 8 pi thirds. That's another way to represent this location using polar coordinates. What if I wanted a negative value for r? Well, if I wanted a negative value for r, I would need to start with an angle that's down here, right? So I would need to think about rotating here and then moving in the negative direction. What would this angle theta be? Well, that angle theta would be a negative pi third, directly opposite, so I would rotate back pi. So this would be a negative pi third, and then I move that direction would make that a negative 4. So that's another way to represent that. I could choose to rotate in a counterclockwise direction all the way here, and that would give me a positive theta with a negative r. Well, this positive theta would be, this is just pi thirds, so this would be 5 pi thirds. So this would be a 5 pi thirds, and then I would have a negative 4 to rotate 5 pi thirds and then move a negative 4. So that's 1, 2, 3. That's what we were asked for, at least 3 other ways. And I could just keep going. I could keep adding rotations to each of those. So you see I have 2 with positive values of 4, 2 with negative values of 4, and I could keep adding 2 pi k to get to new coordinate pairs for polar coordinates. Now my math lab is going to ask you, it's going to specify kind of where it wants that polar coordinate to land. It will say something, let's see, my math lab will frequently ask, it will give you some instructions, and it might say, for example, that r needs to be less than 0, so it wants a negative value for r. and it will tell you kind of what quadrant it wants theta to be in. For example, theta is going to be between negative pi half and positive pi half. So this is just an example, but watch for those instructions for which pair of polar coordinates my math lab is looking for. Okay, so let's look at the next page. In summary, now we're going to do this summary. I don't want you to worry about memorizing this. This is kind of a conceptual understanding of where we need to go. But a point with polar coordinates r theta can also be represented by either taking theta and adding 2 pi k, rotation in either direction, clockwise or counterclockwise, or changing r to negative and rotating it a half turn and then any rotation from there, where k is any integer. The polar coordinates of the pole, 0 theta, where theta can be any angle. So that's just defining our starting place. Now again, don't memorize this. We are working on conceptual understanding. You need to be able to, you need to know how to find those other coordinates without trying to plug it into an equation, okay? So this helps us, if you get stuck, to go back and kind of remind yourself of what we were doing, but I want you to be able to think through these things. This means there are an infinite number of ways to represent a point in the polar coordinate system, which is different from our rectangular coordinate system where there's only one way. We talked about this at the beginning of this section. Okay, so how do we go back and forth? If we are given polar coordinates, how do we get our rectangular coordinate? If we're given a rectangular coordinate, how do we get to a polar coordinate? Well, our link is through our definition for sine and cosine in our right triangle, not our right triangle, excuse me, in our standard position. SOHCAHTOA. So sine theta and cosine theta, where I have x, y, and r, I know that cosine theta is x over r, and I know that sine theta is y over r. Well, let's solve for x here, and let's solve for y here. This would give me x is equal to, if I multiply both sides, I get r cosine theta, and y is equal to r sine theta, sorry. That's what I'm going to use. In rectangular coordinates, my coordinate pair is xy. Well, how do I switch them to polar coordinates? I replace x with r cosine theta, and I replace y with r sine theta. Okay, so let's do a couple of these conversions. Let's think about where this angle would be. We've got two different angles that we're going to change. We're starting with the polar coordinates 5 pi fourth. Well, my angle pi fourth is here, and 5 would be 1, 2, 3, 4, 5, right there. So that is the location of this polar coordinate. Sorry guys, I always do that. That would be the location of this polar coordinate. We want to change, because we're given polar coordinate, we want to change it to a rectangular coordinate. So we are going to use these two equations where x is going to be equal to r cosine theta and y is going to be equal to r sine theta. So x is going to be 5 times the cosine of pi fourth, and y is going to be 5 times the sine of pi fourth. Well, what's the cosine and sine of pi fourth? That's one of our special angles on our unit circle. So x is 5 times the square root of 2 over 2, and y is also 5 times the square root of 2 over 2, because it's a pi fourth, right? They're the same. So our rectangular coordinate here is 5 square root 2 over 2, 5 square root 2 over 2. Does that make sense? It asks, was this what's expected? Well, if I think about these two values, they're both positive, so that puts me in quadrant 1, equidistant, so equal distance on the x, equal distance on the y. Yeah, that's what I expect. Okay, so let's look at B. In B, we have -2, 5 pi 6 as our polar coordinate. 5 pi 6 is almost pi, so it's going to be right over here. It's just a sixth of an angle away from pi. That's my theta, 5 pi 6. And then I need to rotate to -2. Well, -2 means I'm going to go back the other direction, so that would be right here in quadrant 4. Okay, let's use our equations to find x and y. X is r cosine theta and y is r sine theta. So for this one we have -2 times the cosine of 5 pi 6, and for y we have -2 times the sine of 5 pi 6. Now 5 pi 6 is up here in quadrant 2. Cosine is negative, sine is positive. If I use my unit circle or I have it memorized, either way, the cosine of 5 pi 6 is a negative square root 3 over 2. And the sine of 5 pi 6 is a positive 1/2. So the coordinates I get, therefore, are a positive square root 3 and a negative 1. So square root 3, negative 1. That's the rectangular coordinate pair I get for this point. Does that make sense? I've got a positive x, negative y. Absolutely, that makes sense. Okay, let's look at the next page and explore some more with these polar coordinates. Plot the point. Okay, so we're going to be converting from rectangular coordinates to polar coordinates. We're going to be going back the other way this time. Plot the point -6, 0 on a rectangular coordinate system. Well, -6, 0 is right here. Superimpose the polar axis on this system. So think about if this is a polar, if this were on a polar coordinate system, we would be having, we'd have these concentric circles. We'd think about rotating this. So I would have rotated from here all the way there. So that would be my angle right here. Right? What could this point be as a polar coordinate pair? Well, if I think about it rotating here, I would have rotated pi, and that would be a positive 6 if I landed on pi. Or I could think about it as having rotated a full 2 pi, or I could have rotated a full 2 pi and moved backwards so that that r is a -6. That's just two different ways to represent this location with polar coordinates. Okay, let's do this one. 0, -4. Think of plotting 0, -4 on the rectangular coordinate system. That would be this point right here. Well, how could I write that as far as polar coordinates? Well, I could think about it as rotating through this theta and then a positive 4. Well, that theta would be 3 pi half, and that would make r positive. And it asked me to represent this location in 4 other ways. Well, okay, so if I keep 4 positive, I can either rotate through 3 pi half, or I could do a negative pi half and keep 4 positive. I could rotate another full rotation. So I could do a full rotation, so 2 pi plus another pi half would be a -5 pi half and keep that a positive 4. I could do the same here. I could add a full rotation. So that would be 7 pi half. So that would be 4 and 7 pi half. Or I could think about rotating, I could rotate here just a positive pi half and then move a -4. So another location would be a -4 positive pi half. I could do a full rotation plus that pi half. So that could be 5 pi half and a -4. Oh, that's 5 instead of just 4. So you can see we quickly come up with multiple polar coordinates for that one location where we were given a rectangular coordinate. Okay, now we're going to go from rectangular coordinates to polar coordinates with a point in a specific quadrant. So that was when I had a quadrantal. Now let's look inside a quadrant. Plot the point -3, +3. This point, -3, +3, is in quadrant 2 because x is negative, y is positive. From the pole, draw in the polar axis and the terminal side of the angle. So my polar axis is here. The terminal side of the angle would be here, right? So there is my angle theta. And, you know, this is however many units are out. So the relationship of x, y, and r, x, and y, is going to be r squared equals x squared plus y squared. This is my r value, just like always, right? How do I find r? Well, r equals the square root of the sum of the squares of the coordinates. My coordinates are -3 and 3, so -3 squared plus 3 squared gives me the square root of 18, and that will simplify because 18 is 9 times 2, so that simplifies so that r is 3 square roots of 2. Now, hopefully we can recognize what my value theta is here, but what if we can't? Well, the relationship between theta, x, and y, what we're going to use for that is going to be tangent theta equals y over x. Notice that we're using our given values, not our found value of r. So we're always going to be using tangent theta equals y over x to find theta. Now remember that if I'm having to use my calculator and tangent is negative, I'm going to have to potentially add pi, because if I'm using my inverse function on my calculator, tangent is defined for quadrant 4 and quadrant 1. If I have a negative value of tangent, it's going to return an angle in quadrant 4. If the angle I need is in quadrant 2, I have to add pi to rotate that around. Let's, I guess, write that out, because tangent inverse is defined in quadrants 4 and 1. Okay, so we're going to use tangent theta to find our angle. So tangent theta equals, tangent theta equals y over x, and we were given y as +3, x as -3, which gives me a tangent function value of -1. This is a special angle on my unit circle, so we don't have to use our calculator. We know, because we're in quadrant 2 and we have a tangent function value of -1, that our angle is 3 pi fourths. That means that my polar coordinates, r theta, are 3 square root 2, 3 pi fourths. Now, that is one pair of polar coordinates. That's the basic one that I get, and then I could come up with multiple different values for that. Okay, this is going to be a little bit of kind of an extension that's going to get us ready for what's coming up. In the next section, polar coordinates are going to be graphed. Polar equations will be graphed. Polar equations have r and theta. They can be derived, we can come up with a polar equation from our rectangular equations where I have x and y, two different ways. Now, we have to use a little bit of conceptual understanding here to figure out which way we want to use based on what we're starting with. The first technique that you might use is to square both sides. The second technique that you might choose to use would be to multiply both sides of the equation by r. You're going to use one of these methods, so we're going to practice. We're going to use one of these methods to transform the equation r equals cosine theta from polar coordinates to rectangular coordinates. Now, we are looking for things that give us substitutions. So when we're picking which method to use, we are looking for the method that will lead to substitutions. We're looking for the method that will lead to some substitutions that we can make. Okay? And it may be a little bit of trial and error. But I see that, you know what, I'm trying to get this in the form of x and y instead of r and cosine theta. If I multiply both sides by r, we're going to choose to multiply both sides by r here. I have r squared equals r cosine theta. Now, I can I have substitutions for this to get this in terms of x and y. R squared is the same thing using my Pythagorean theorem. We're going to substitute here. Substitute. R squared is the same thing as x squared plus y squared. And r cosine theta, if we think about changing to rectangular coordinates, well, that is x. Now I want to put this in standard form, so I want to set it equal to 0. I'm going to move that x over, which gives me x squared minus x plus y squared equals 0. That's my standard form. Okay, we're going to practice this a couple of times. And again, this isn't something that I expect you to just magically know. This is something that we're working on. So, oh, you know what? We need to talk about the equation of a circle. They introduced this. We have not yet talked about the equation of a circle. So let's come down here to the bottom where we have some blank space, and let's add a definition. Equation of a circle looks like x minus h quantity squared plus y minus k quantity squared equals r squared. So if your circle is centered at the origin, it's just x squared plus y squared equals r squared. This allows me to transform to shift the center. This gives me a center at hk and a radius of r. So this is kind of my graphing form of the equation of a circle, where the center of the circle is at hk and the radius of the circle is r. Okay, now let's go back up. So for this first one, we have r equals 5, and we need to get it into terms of x and y. If I multiply by r, I have r squared, that's nice, but 5r does not help me. So instead of multiplying by r, let's try to square both sides. If we square both sides, we have r squared equals 25, and then I can do a substitution here. R squared, remember, Pythagorean theorem, is the same thing as x squared plus y squared, so that I have x squared plus y squared equals 25. Standard form is x squared plus y squared minus 25 equals 0. That's my standard form. And if you look at this form and you think about that equation of the circle that I just gave you, this is going to be a circle with a center at 0, 0, because x squared plus y squared, I'm not subtracting or adding anything to those. And then 25, remember we said r squared where the radius is r, so the circle would have a radius of 5. Okay, let's look at B. R equals 4 sine theta. R, I can't do anything with r, so let's try multiplying both sides by r here. If I multiply in both sides by r, I get r squared equals 4r sine theta. Substitution. R sine theta is y, so that's 4y. R squared is the same thing as x squared plus y squared. So if I move everything over to the left for standard form, I have x squared minus 4y plus y squared equals 0. That's my standard form for my equation. What if I want to know what this looks like in terms of a circle? Well, if I want to find the equation of my circle, I would need to complete the square. Let's just do that. Complete the square to find the equation of the circle. Now, I need to complete the square for the y's, not for the x. That x squared is fine. So let's just leave the x squared there, and then we're going to complete the square with the y's. Oops, sorry. So I've got y squared minus 4y, and I need to think about what I need to add to both sides to make a perfect square trinomial here. If you think back to your college algebra, complete the square, you take half of b, and then you square it. Well, half of negative 4 is negative 2, and I square that, and I get plus 4. So I add 4 to both sides of the equation. Now this is a perfect square trinomial, and it is factorable into two identical factors. What do I multiply together to get y squared minus 4y plus 4? Well, remember that half of b was negative 2? That's my factor. Y minus 2 quantity squared gives me this perfect square trinomial. Y squared is y times y is y squared. Multiply them together times 2, and I get that negative 4y. Negative 2 squared is 4. So I complete the square by creating a perfect square trinomial, keep my equation balanced, then I factor it, and I've got the equation, the graphing equation for my circle. The center of my circle is going to be at 0, 2, because remember my equation says I start with x minus 2 quantity squared, y minus 2 quantity squared. So the center is at 0, 2, and the radius of this circle would be 2. So that is the circle that I would graph from that equation. Transforming an equation from rectangular to polar form. So now we're going to do these last two going back the other direction. On A, we have y equals 3, and y equals 3 is just a horizontal line. How can I put that in polar form? Well, y is r sine theta, and we're done. If I wanted in standard form, I would say r sine theta minus 3 equals 0. That's fine too. What about over here? We have y squared equals 3x. This is a parabola. If I were going to graph this, this would be a parabola on its side. It's going to look like this, right? Okay, how can I get that into my polar form? Well, y squared is the same thing as r sine theta squared, and x is r cosine theta. Let's distribute this 2 inside so that we have r squared sine squared theta. If we move that over, 3r cosine theta equals 0. That is my standard form. If I wanted to simplify it some, I could. I could factor out the r here. R times r sine square theta minus 3 cosine theta equals 0. Now, if I tried to factor this and I said r equals 0, that's not possible, right? Because r equals 0 gives me nothing to graph. So I could just simplify it to this. And if I wanted to solve for r, I could say r equals, move that over, 3 cosine theta divided by sine square theta. So that would be a simplification of what I had. I think my math lab is going to let you stop right here, though.